Alright, chemistry, this lesson is on measures of concentration. So a mixture consists of a combination of two or more substances. Mixtures can be homogeneous, meaning any part of the mixture is the same as another part. So think of a pitcher of Kool-Aid. The first glass you drink tastes the same as the last because the Kool-Aid powder is mixed homogeneously throughout the pitcher. A heterogeneous mixture is not uniform throughout. Think of a fruit salad. One spoonful might have a grape and a pear, while another spoonful might have a banana and a strawberry. There are three types of mixtures in chemistry. Solutions produce molecular-sized particles of a solute that are dissolved in a solvent to produce a homogeneous solution. Colloids produce particles in size between 1 and 1,000 nanometers, and colloids usually stay suspended in the solution. And finally, suspensions contain particles larger than 1,000 nanometers. Often the particles of a suspension settle on the bottom of the container. So since chemistry deals with interactions on an atomic and molecular level, we will speak only of homogeneous solutions in this class. So a solution consists of a solute dissolved in a solvent. So if you think of making a pitcher of lemonade, the lemonade powder is the solute. It's what gets dissolved. And it has 6 letters in its name. The water is the solvent. It's what does the dissolving. And that word has 7 letters in the name. And finally, when you put the two of them together and stir, you have a homogeneous solution. And that word has 8 letters. The significance is the one with the least number of letters, solute, is the one that you have the least of. That's the lemonade powder. The one in the middle, solvent, that has 7 letters. And then the one that has the longest word, solution, 8 letters, that's both of them mixed together. So when one substance is mixed into another, it is called a solution. When a substance is mixed into water, it is called an aqueous solution and is designated by the symbol AQ. The amount of solute used in relation to the amount of solvent is called the concentration. The primary measure of concentration is molarity, abbreviated capital M. So molarity is the moles of solute over the liters of solution. A key is that it's over liters of solution, the two of them mixed together, not liters of water, H2O, liters of solution. So it's moles of solute over liters of solution. So if glucose, C6H12O6, is dissolved in water, we have the following. The solute is the glucose, the solvent is the water, and the solution is the two of them mixed together. Usually we represent solution with the letters SOLN. So a 2 molar solution of glucose is 2 moles of glucose in 1 liter of solution, where SOLN represents the two of them together, the glucose and the water. So here we have a beaker. So imagine that each group of 10 CO2 molecules down below in the beaker represents 1 mole of CO2. And it's homogeneously mixed in 1 liter of solution. So that's the entire beaker is 1 liter. So there's 1 mole, and there's 1 mole. So you have 2 moles in 1 liter of solution. So assume that the beaker has 1 liter. A 2 molar solution has 2 moles of solute, CO2, in 1 liter of total solution, the two of them mixed together. That's a homogeneous mixture. So the particulate diagram represents 2 moles of CO2 molecules in 1 liter of water. So this is a molar concentration of 2 moles CO2 over 1 liter of solution. That would be a 2 molar solution. So assume that the solution is homogeneous. What would be the molar concentration if we poured half of the solution from the beaker? So you have your pitcher of lemonade and you pour half of it out. What would be the new concentration? So there we did it. We poured half of the solution out of that beaker. So now we have half a liter of solution and we have 1 mole of CO2 are gone. So what's the new concentration? Well, when you do the math, it's 1 mole of CO2 over half a liter, which is still 2 molar solution. It's still a 2 molar concentration, the same as it was before. In other words, again, if you take your pitcher of lemonade and pour half of it around to people in the room and still have half of it left, the second half is going to taste just like the first. The taste is the same. You haven't changed the concentration. So the concentration would not change. So think about a pitcher of Kool-Aid. The first cup tastes the same as the fifth cup. This is because the concentration in each cup is uniform, the same. Okay, so here's the molarity, the formula for it. Now, there's other measures of concentration that we'll use. Molarity is the main one. We'll probably use molarity 90% of the time. But mass percent, we talked about that in the context of compounds and how much carbon, what the percentage of carbon, what the percentage of oxygen, but you can do it with solutions. It's the grams of solute over the grams of solution. That'll give you a decimal number, and that's times 100%. That would be the mass percent of the solution. Mole fraction. Mole fraction is similar, except it's moles of one solute over moles of all the solutes and the solvent put together. You don't multiply this by 100%. You just end up with a decimal number. And we'll use mole fraction somewhat frequently in the class later on. Then there's parts per million. That's very similar to mass percent, but it's not, instead of being times 100%, it's times a million. You use that for very small concentrations, like the particulate matter that's in drinking water, like arsenic and lead, things that are harmful, but if they're in small enough concentrations, it's not unsafe to drink the water. And another one that's important is dilution. It is basically if you start with a certain molarity and a certain volume and you add water. So this is you made the lemonade too strong. So you add some water to make it weaker. That's called dilution. And so the molarity before times the volume before equals the molarity after times the volume after. It's a very simple formula. Now, density is defined by the amount of mass contained in a volume. In solution stoichiometry, it usually means grams of solution per milliliter of solution. So often density is stated in the problem as follows. The density of salt water is 1.09 grams per milliliter. Now you can convert that into an equivalency the way we like to do in doing stoichiometry. So this can be represented by 1.09 grams solution equals 1 milliliter of solution, where salt water in this case would be the solution. The conversion factors then, you could have two of them. 1.09 grams of solution for every 1 milliliter of solution, or 1 milliliter of solution for every 1.09 grams of solution, and you just use that like we do any other conversion factor. Note, there is no fixed density for salt water. It depends on how much salt and how much water is used. Mass percent gives the mass of a solute as a percentage of the mass of the solution. It's given by the formula we saw earlier. So you will encounter problems that give a solution in mass percent. Here's an example. A solution is 3.5 mass percent sodium chloride. So we've talked about what you do when you're given a percentage. Since the problem does not say what mass is used, you get to choose, and you will always choose 100 grams of solution. So since the problem does not say what mass is used, you're going to choose 100 grams. So 100 grams of 3.5 mass percent sodium chloride solution will contain 3.5 grams of sodium chloride, and the rest would be water. So let's prove it using the mass percent formula. So 3.5 grams of NaCl over 100 grams of solution times 100% gives you 3.5%. So we talked about this relationship in converting a percentage into a number of grams by choosing 100 grams of solution. Okay, remember when you are given a mass percent problem, rather than a number of grams or moles, choose 100 grams of solution and the grams of solute will equal the mass percent. All right, and that takes care of this introduction to solution stoichiometry. It's actually the kind we're going to use most frequently in lab and in experiments.